Okay, this is Leetcode 3290 maximum multiplication score. So you're given an integer array A of size 4 and another integer B of at least size 4. And you need to choose exactly 4 indices from array B such that indice 0 is less than indice 1, is less than indice 2, and so on. Your score will be equal to the value A at indice 0 times B at whatever your indice 0 that you choose, and so on down the line. And you need to return the maximum score you can achieve. So all this is saying here is that you need to choose exactly 4 indices, and all this is saying here about the order is you can't just choose, say I'm at this position, if I choose at my 0th index of array A, I choose to multiply index 2 at array B. If I choose to make that multiplication, I can't then on my next index, so index 1 on array A, I can't then choose to use index 0. These two would be completely off limits. I would have to choose something that comes after it. So that's all this is saying in here. And so anytime you see like return the maximum score you can achieve, you need to think, can I use recursion? Can I use dynamic programming to my advantage here? And this is a cookie cutter recursive to memoization solution. And you might get tricked in the constraints because the constraints, I think, say 10 to the 5th. And if this is 10 to the 5th, obviously, if we're doing a recursive method where we're keeping track of the index that we're currently at in A and the index that we're currently at B, that would technically be n times m, and that would give us a time limit exceeded. However, we're guaranteed to have array to be of length 4. So really this gets cut down to n times 4, which will pass on Leetcode. So to get into the actual, as we will get into the actual problem walkthrough, obviously decision trees are pretty clear, but all we're going to really do is we're going to try at each index here, we're going to try at each index to try each possible combination in array B with whatever index we're at here. So if we're at index 0 here, we're going to try to start it at every single index in array B. And obviously we need exactly 4, so we can't, we technically we'll just return, for these we'll just return negative infinity if we ever start it at an index where we know we can't get through our entire array. So if we ever get to the end of array B without getting to the end of array A, we know we can just return negative infinity. So we're going to just try each combination for index 0, and then we're going to try each combination that comes after whatever we choose for index 1, and then we're going to try each combination whatever comes after for index 2, and so on. And we'll keep track of where we're at in array B and in array A, and we can then use some memoization to speed this up. So quick walkthrough, we'll do a quick walkthrough on this one. So we'll first try to multiply 3 times 2. That gives us 6. And we're adding this to whatever comes next. So what will happen is if we do that, if we perform that, we'll move both indexes, so I and j, to the next index. And then what we'll do is we'll add whatever, we'll try, obviously we're trying every possible combination here. So it would be very lengthy for me to go through every possible combination. But I believe the right answer here, actually, we end up multiplying 2 by -6. So we'll add 2 times -6, which is 12. And we'll add that to, it's -12, so we end up getting -6 here. And then the next, now we have this 5 here, we end up multiplying, because we've moved both over, we end up multiplying 5 by 4, which gives us 20, and that ends up equaling 14. And then what we'll do is we'll try every combination. After we move these over, we'll try every combination. We'll try 6, -5. We'll try 6 with -3. We'll try 6 with 2, and we'll end up returning as our max. We'll end up returning 6 times 2, which gives us 12, and our answer ends up being 26. So that's the walkthrough, and the coding solution I'll walk through kind of the recursive solution, and then I'll walk through how we can optimize this with our dynamic or memoization solution. And then for time complexity purposes, like I talked about earlier, we're able to, the recursive solution obviously is exponential because we have an exponential amount of branches that we could potentially go down, and we can get that down to O of n, with n being the size of array B. And this is because this is technically O of n times 4, and we drop constants. So this will be our time complexity, and for our space complexity, it will be the same thing. O of n times 4, and that is because we are holding whatever is in here in our memo, and that will take up the majority, or that will take up our space. So we will be using O of n. These can both get simplified down to just O of n, so O of n time, O of n space. Now, for the coding solution here, what I'm going to do is I'll walk through recursive, brute force, and then we'll optimize. So what I like to do is have depth first search make it a local function inside kind of this global solution method. And what we're going to need to do is we're going to need to have I and j, like I talked about earlier. And the number one thing that we're gonna know is we don't have to get to the end of B to return a valid solution, because here this would be a valid solution. All we have to know is if we've gotten to the end of A. So if we ever reach the end of A, we can always return. So if I ever equals the length of A, and then if we ever get to the end of B, we know we have to return, we know we have to break out of whatever we're at, because to return some type of false, which here we'll return negative infinity. So if j equals the length of B, we'll return float of negative infinity. And again, that's because we know if this didn't return, we know we're going to have to return false, because we're not at the end of our A. So this is the equivalent of false. And so the next thing that we'll do is what we'll need to do is all we'll do is we'll take, we have two decisions here that we need to make. So we either take or we don't take. And if we take, we need to move I forward. if we don't take, we need to only move B forward. So in this case, what we'll do is we'll have a depth first search here where we do take. So if we do take, we'll move both forward. And when we do that, we need to add our multiplication to this. So we'll have A of I times B of J, and we'll add the answer of that to whatever we're our cumulative answer here, so whatever we're accumulating. And then if we don't take, all we'll do is we'll just say depth first search of I, and then we're going to only move J forward. And for both of these, we'll just have them first be float negative infinity, and we'll just return the max of whatever these are. And all we have to do is then return our depth first search and call it. And this should work as the recursive solution, 26 and -1, which are our two answers here. So then how to speed this up? Obviously this, we're doing a lot of repeated work here because we're going down trees where we're going down branches of the tree that we already know, we've already calculated that answer before. So what we want to do is we want to save those partial answers in our memo, and that can cut our time complexity down. So our memo is going to contain both I and J, because we need to save the state somehow. So we'll say if I, J in memo, we'll return the memo of IJ, and then we'll take this and whatever we save as our max here, we'll save that into our memo, and then we'll return the memo here. So let's try this again. This works, and let's submit it. And there we go, accepted. So this was maximum multiplication score.